Today we're going to be talking about the mean of the binomial distribution. So formally the expected value is going to be x times by p of x, but this is the probability distribution for a binomial distribution, and that's how we calculate p of x. Now this formula is kind of a little daunting, so there's another way that we can calculate the mean, and that's by taking the derivative and evaluating it at 0. We're going to use the fact that the moment generating function here is given by this formula, q plus p e to the t raised to the nth power. Okay, and q is equal to 1 minus p. It's the probability of failure. So if we want to differentiate this, we're going to have to use the chain rule. We're going to take the exponent and bring it down, so it'll be n times by what's inside. So q plus p e to the t. The new exponent is 1 less, and now we have to multiply by the derivative of the inside with respect to the variable t. Q is a constant, so its derivative is 0. The derivative of p e to the t is just p e to the t, because the derivative of e to the t is e to the t. Okay. Now, if we set this equal to 0, that is the value of t, we're going to calculate this. So this will be n times q plus p e to the 0. And remember, e to the 0 is 1. We're going to get n times q plus p times by p. And now, using the formula that q is equal to 1 minus p, if we substitute that in and use that relationship, we're just going to get n times p, and this is the expected value, or the mean, of a binomial distribution. If you were asked to calculate the variance of x, you can calculate it as e of x squared minus the mean squared. That formula applies for any distribution. Now, I would recommend calculating e of x squared by calculating the second derivative of the moment generating function and subtracting 0. Then the mean we just calculated, that's n times p quantity squared. Okay. If you do all of these calculations, you're going to get n times p times q, or n times p times 1 minus p. And that's the variance of binomial distribution. Notice I left off the step of calculating the second derivative of the moment generating function that's above. Okay, but I've outlined the steps that you can take to calculate the variance.